Welcome to the continuation of our lectures in physics tailored from Jamb syllabus. Okay, so today we are continuing with production and propagation of wave. Please do well to get your pen and your notebook to jot what you understand in this lecture, because you are definitely going to need it for your subsequent revision. Do not just take this lecture without jotting down. I beg you, for your own good. Now, let's look at production and propagation of wave. Number one, we have to understand wave motion. What is wave motion? Wave motion is a disturbance that travels through a medium or space. It can either travel through a material medium or through space. The space is what? The atmosphere. That's space. The atmosphere, the air, that's space. So it can either travel through a medium, maybe through a solid, a liquid, or through space, which is the atmosphere. And as it travels, it transfers energy without transferring of what? Matter. So as the wave continues to transfer energy, it does not cause any permanent disturbance to the medium. So wave transfers energy, but it doesn't transfer matter. So wave is a disturbance that travels through a material medium or space, transferring energy as it moves, okay, without causing any permanent disturbance to the medium itself or without transferring matter. So now let's look at the vibrating system as a source of wave. If you talk about the vibrating system as a source of wave, you are going to look at examples like tuning fork. You know the tuning fork, now the vibration of the tuning fork. It's usually used to detect the extent of sound or the intensity of sound and so on and so forth. So you are still going to talk about the stress string, okay? The stress string of a guitar, the stress string of a solenoid, you know a solenoid coil with string instruments, various string instruments, okay? So that's it. For example, like piano. Piano is also a string instrument. That's when we are talking about the vibrating system as a source of wave. So when you strike the strings of any of these instruments, you are going to in turn see a wave, But after the wave has been transmitted, or after the wave has been transferred, you know, as the wave is being transferred, energy is also transferred. It is that potential energy, most of the time is kinetic energy that is transferred. You are going to see moving energy, oscillation, because of wave, oscillation most of the time. So it transfers energy, yet it doesn't cause any permanent disturbance to the medium itself, to the string itself. No permanent disturbance to the string itself. When the wave finish passing, or when the wave has been transferred, the string remains the same. So that's it. Other examples like loudspeaker, vibration. Loudspeaker diaphragm, that diaphragm of speaker, that thing that used to be like this. If you get all those JBL or Zillow speaker, if you play, that thing that will be doing like this, that's what it's called diaphragm. That thing that will boom, 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 boom. That thing that will be shaking but moving, to and fro movements, oscillating. So another one is a ripple tank. Remember the ripple tank experiments used to experiment small wave. When you throw a stone inside a small bowl of water, you are going to notice a small wave, or what is called the water wave, a ripple. As a result of that stone you throw inside the bowl of water, you are going to see the ripple, that rebound of water, okay, that outflow of water that follows the path of the stone, or the place the stone came from, okay. If you throw the stone here, it's going to try to trace the source, the path where the stone was thrown from. That's the water wave demonstrated with a ripple tank. So now let's look at wave as a mode of energy transfer. Wave as a mode of energy transfer, energy moves from source to medium without permanent displacement of particle. I told you, without permanent disturbance of the medium itself. So wave is transferred from the source to the medium without permanently displacing the particles of the medium itself. Now let's look at particle motion versus wave motion. Remember that there's this scientist called Heisenberg. He made a postulation years back that waves behave like particles and particles behave like wave. That's the postulation of Heisenberg, the uncertainty principle, okay. So that tells you that wave and particle has some similarities, okay. So let's look at the difference between particle motion and wave motion. They have similarities, but they are not equally the same, okay. So the particle motion, particles, the kind of motion exhibited by particle is oscillation about equilibrium. So oscillation about balance. There's always balance in the movement of particles. But when you come to wave motion, we already described wave motion. Wave motion is a disturbance that travels. This one, he said propagates here. That's multiply. It travels through medium. There's a medium. It travels through a medium. That's wave motion. But particle motion is just oscillation about a balanced place. Something will just happen for a balanced place. That's particle motion, particle vibration, particle motion. That's it. Let's look at the relationship between frequency, wavelength, and velocity. The relationship between frequency, wavelength, and velocity is V, which is the velocity, is equal to what? Frequency times lambda. And lambda means what? Wavelength, or lambda signifies wavelength. So V, which is the velocity, is equal to what? Frequency, which is F, times wavelength, which is what? Lambda. This thing that is here is lambda. So let's take, for example, Jamb asks you a question. Jamb says you should look for, give you a question, you've looked at the question is related to wave, and they tell you to look for the velocity of the wave, okay. So what are you going to do? Use this formula and you substitute wavelength and frequency. Okay, but what if they tell you that you should find wavelength? What are you going to do? You do what I taught you. You make what? This wavelength the subject of the formula. You bring it to this side. So the in-turn formula becomes what? F over what? V. And you get your answer, Shikina. Making of subject of formula. The same thing for F. If they say you should find frequency, what is the frequency? All you have to do is you bring frequency to this side. But if they say you should find frequency, that's if you were given wavelength and velocity, because the formula for frequency is 1 over t, which is 1 over time. F frequency is equal to 1 over time. But if you were not given time there and you were told to look for frequency with this, you bring frequency to this side, then you are not going to be left with what? You're not going to be left with lambda over v. Okay. Now let's look at the phase difference. Okay. What is phase difference? Phase difference is the difference in phase angle between 2 points on a wave. That's as simple as ABCD. Now let's look at wave number, which is small letter k. Wave number, small letter k, is equal to 2 pi over lambda. Put this formula inside your head. 2 pi over lambda. Wave number, 2 pi over lambda. If you want to solve now, if you have your lambda already, your wavelength, what do you have to do? You substitute now. Very easy. You don't know what is 2 pi. 2 pi for primary school, which is 2. This one, pi is 22 over 7. 2 is what? 2. You times them by 22 over 7. What do you get? Use and divide this lambda. You get your answer, Shikina. Use and divide wavelength. For here, you get your answer. So let's look at wave vector. Wave vector is the quantity showing direction of wave propagation and magnitude. So as simple as that, you all know what vector quantity is. We've treated that before. So vector is a quantity that has what? Magnitude and direction. Both magnitude and direction. So when you say wave vector, is the wave quantity that has what? Movement. And it has a direction. As easy as that. And magnitude is equal to what? Wave number. Magnitude is directly proportional to wave number. If you are told to look for wave number and you have magnitude there, pick magnitude and you are good to go. That's the answer. Because magnitude is equal to wave number. So if you are giving wave number and magnitude and you are being asked to find the wave vector, what do you have to do? You already have the magnitude and the direction. You divide both sides and get your answer. You divide wave number by magnitude and you get your answer. As easy as that. So progressive wave equation. This one is another one again. Jamb, like this. Now so Jamb take carry and paste for their syllabus. Okay, that is a sign of something. So ensure you learn this progressive waves formula. It's very easy, hard. Y equal to a sine bracket open 2 pi over lambda times this one s plus or minus depending on what you are calculating, vt, where this a here is equal to amplitude, then v here, this v is equal to what? Velocity, and what? This one lambda here is equal to what? Wavelength. Look at it here, wavelength. Okay, we show that in the s is the number of wave. So if you are given a question in your Jamb UTME and you are told to look for the progressive wave or the wave induced from a particular point to another, apply this progressive wave formula. It's very easy. A sine bracket open 2 pi over lambda times s plus or minus vt. So where you are going to use minus or plus depends on, is the wave accelerating or is the wave decelerating? Is it an accelerating wave? Is it something that is going forward? Or is it something that is bringing something backward or that is going backward? That's what's going to determine if you are going to use plus or minus. If it's a wave that is taking something forward or that is moving forward, you use plus. That's, you put plus here. But if it's a wave that is taking something backward or that is moving backwards, you use minus to calculate progressive wave. All these things very easy. Now let's look at the classification of waves. The first classification of wave we have here is mechanical wave. And what is mechanical? You know what mechanical means now? It involves a mechanism. Mechanical wave requires a medium. Any wave that requires medium is a mechanical wave. For example, you have sound wave, you have water wave. Both of them requires medium. Water wave requires water. Okay. Sound wave requires solid to be transferred. It might require liquid to be transferred. It might also require air to be transferred. Okay. There's the speed of sound in solid, there's the speed of sound in liquid, and there's the speed of sound in air. Sound has varying speed or velocity in these three mediums. Okay. So let's look at electromagnetic wave. The other class of wave is electromagnetic wave. And what's electromagnetic wave? Electromagnetic wave do not require material medium such as light. I think they are the point person light for that side. It does not require a concrete material medium. You know, if you say because a gas no day, air no day, light no go shine. Whether gas day, whether light day, whether light no day, whether water day, whether they build that. So if you on light, you must surely see that light. So that's electromagnetic wave. It includes light, it includes radio waves, and so on and so forth. You get radio signal because it does not need a material medium. Okay, it requires no what? No material medium. You can be receiving signal. Your phone, the network, they enter your phone because it does not require material medium. Okay, your phone receives signal. So that's what electromagnetic wave is. Magnetic. It's magnetic. Transmission of electron through magnets, through magnetic means. Okay, that's electromagnetic. So let's look at longitudinal wave. This is another classification, or the third class of wave is longitudinal wave. Take note of longitudinal wave. The opposite of longitudinal wave is transverse wave. The opposite of mechanical wave is electromagnetic wave. So let's look at longitudinal wave. Longitudinal wave, particles vibrate parallel to direction of propagation. So if I shout now, hey, the particle from my voice, the rebound from my voice, or the wave that is going to be rebound as a result of what I yelled, what I shouted, what I screamed, is going to be transmitted parallel. That's straight back to me, following almost the same path back to me. So if I shout, hey, I will hear it from here. That's why when you are hearing the sound, you can say this sound is coming from this side. You can say this sound is coming from here. Now from here, now that guy make that noise from back. Now your teacher in class will say the noise is coming from the back, the noise is coming from behind, the noise is coming from the front, the noise is coming from that edge close to the door, because it's a longitudinal wave, sound wave. It's a longitudinal wave because it does what? The direction of propagation is parallel. It goes straight. Now let's look at the opposite of longitudinal wave, which is transverse wave. And transverse wave, particles vibrate perpendicular to the what? The direction of propagation. In longitudinal wave, the propagation is parallel. Look at it here. It's parallel. When you say the parallel direction of propagation or multiplication or transmission is like this. It goes like this. This is the path. Okay. But for transverse wave, it is perpendicular. That's like this. Like this. Particle vibrates perpendicular to what? To the what? The direction of propagation. This is how the particles vibrate. So the particles vibrate like this from a transverse wave. Then from a longitudinal wave, the particles vibrate like this. Both of them are oscillation. This is an oscillation and this is an oscillation. Okay? In a bowl of water, I might be creating a wave like this. I will put an object on the other end of the bowl of water, that big bowl of water. I will put an object at the other end, the opposite end. And I'll be here creating a wave like this with my hand, dipping my hand in the water and removing it. I am dipping it like this and removing it like this. But when you look at the wave, it propagates that wave that I'm creating to the other end or the opposite end of that bowl. The wave, I was propagating the wave like this, or the source was like this. But when you look at the object might be displaying a wave like this, a transverse wave. Okay, so I sent a longitudinal wave like this, but in turn, it was propagated as a transverse wave like this. Both of them are oscillation. Both of them are to and fro movements, like this or like this. Both of them are to and fro movements. That's why they are called vibration. And examples of transverse wave include what? Light water wave. Just like the example I just gave you now. Okay? Light and what? Water wave. The particle vibration is perpendicular. That's like this. It travels perpendicular to the direction of what? Propagation, or the direction of transmission. If the word propagation is too big. Then let's look at stationary wave. The opposite of stationary wave is progressive wave. So these 6 waves are the classification of waves. Okay, so let's look at the previous ones. The opposite of mechanical wave is electromagnetic wave. The opposite of longitudinal wave is transverse wave. Then the opposite of stationary wave is progressive wave. Now let's look at stationary wave. I taught you before that when you say stationary, anything stationary means that thing is not moving. It's in one place. Okay, it's stationary. It's not moving. That's stationary. So when you say stationary wave, it means that the wave is not moving. You say produce is a wave produced by superimposition of 2 waves of same frequency traveling in opposite direction. Nodes and antinodes formed. So in stationary wave, nodes and what? Antinodes are what? Formed. So it's a superimposition created by 2 waves of the same traveling frequency. Okay, so because they have the same traveling frequency, the particle of vibration does not move in any direction. It's static, it's stable. Okay, it's stationary. Okay, so this is where you have the nodes and the antinodes. Now let's look at its opposite, which is progressive wave. Progressive wave is a wave that travels continuously through material medium, transferring energy. It travels progressively through a material medium, transferring energy. For example, sound wave is a progressive wave. The water wave I just did, when I talked about the water, I'm here, and at the opposite end of the water, that wave is propagated to that object there. The object is feeling it from the water. So I can come to a river now, or an erosion water we gather for somewhere. A stagnant water from gully erosion, maybe water that is not moving, more like a lake. And I just go there and just throw a stone inside. As I throw that stone, you are going to notice that the wave continues to spread continuously. That's an example of progressive wave. Okay, so now let's look at examples of progressive wave. Okay, we have spring, you have rope. Okay, when you hold a rope like this, you do it like this, the rope will continue to show you that wave. It continues to progress. Spring, when you do a spring like this, the wave continues to you understand, it continues to propagate the wave continuously, transferring energy through a material medium, because a material medium is required, or a medium is required. So stress string, That's that for that too. You have ripple tank, like the one I just demonstrated for you, used to demonstrate reflection, refraction, and diffraction interference. So all you see here, this demonstration, reflection, refraction, diffraction, and interference, they are all characteristics of wave, and we are going to discuss them next. Having understood the types and classes of wave, let's look at the characteristics or properties of wave. The first characteristic we have here, or property of wave we have here, is reflection. And what is reflection? Like the name implies, it means that wave bounces back off a surface. Okay, you point touch for wall now or for mirror, it bounces it back. Okay, it bounces it back, especially a shiny surface. Okay, like the mirror, the way the mirror bounces your image back to you. The light ray, when you stand in front of a mirror, the light ray from your surrounding falls on your skin or on you. As it falls on you, your skin bounces off that light ray, and it falls in what is in front of you, the mirror. And when those light rays fall in front of the mirror is going to do what? Because it's highly reflective, it bounces back your reflection or the light ray that falls on it, and that is your reflection, and that's what you see in the mirror. And as it bounces it back, and when you look at it, the light ray that bounces off the mirror is going to enter your pupil and go straight to your retina, and your retina is going to what? Form an image, and your brain interprets it and say, this is me standing in front of the mirror, this is my picture, this depicts me. That's how it happens. So that's reflection. So the second characteristic here is refraction. And what is refraction? Is the change in direction when wave passes into medium of different speed. That change in direction you get when a wave enter into a medium of different speed. For example, a tire of the car was moving, okay? The material medium that transferred the wave to the tire, that make the tire to be moving the vehicle, to roll it from the shaft that connects to the engine. That was the first material medium, okay? That the wave is being transferred from the engine to the car wheels, okay? Then when the tire pulls, for example, as the car is in motion, the tire pulls off, for example, the medium of the transmission of the wave has changed, and it now has a new speed. Okay, so the direction of the wave is going to change. That's why when the tire pulls off, the tire no go come the road the way they roll again when you did the motor. Okay, you know the road the way they roll again, way they for the car, with the roll scatter any direction, if even the bounce, bam, 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 bam. So it's the change in direction when wave passes into a medium of new speed. Okay, so let's look at diffraction. Diffraction is the bending of waves around obstacle or through narrow openings. For example, this place bend like this. I point touch for where bend like this. When the wave gets to that point, it's going to do what? It's going to bend. Okay, because of the point, that's diffraction. It bends. Okay, it bends because of obstacle. When you put obstacle in the path where a wave passes, it bends. That's diffraction for you. Let's look at plane polarization or polarization. Okay, and this is a characteristic of wave. It means restricting vibration of transverse wave to one plane. The vibration of the transverse wave, you know what a transverse wave is now? The one that travels perpendicular like this. So when you resist the travel of a transverse wave, or the particle vibration of a transverse wave, you restrict it to only one plane. That's why it's called plane polarized. You polarize it, you make it to be perpendicular into only one plane, through one plane. The final one we have here is superimposition. And what is superimposition? Superimposition is when two or more waves overlap. Either they meet or they overlap. When two or more waves meet or what? Overlap. That's what superimposition. And what? Resultant displacement is equal to algebraic sum. And this principle of superimposition also work with another characteristic of wave that is not here, called interference. Okay, interference is an occurrence or the characteristic of wave whereby the two waves meet or overlap. When two waves meet or overlap, they either meet like this and overlap, or they meet and overlap. So for interference is when two waves meet or overlap. Okay, so they meet during propagation, maybe like this, and they overlap. Okay, and when they overlap, they can either draw closer or they move apart from each other when they overlap. And there are two types of interference. We have the constructive interference, where when the two waves, when they meet, they come together. Okay, and the destructive interference, when the two waves meet, they move apart. Okay, they overlap and move apart. They overlap and move apart. That one is the destructive interference. So this diffraction, you can define this diffraction as the bending of waves around obstacles or through a narrow opening. Yes. So you can also, this diffraction is also when you pass a wave through an opening, it spreads. Okay, it spreads. That's diffraction. When a wave is passed through a small opening. For example, I carry light. I point them through this small hole. Okay, I point light through this small hole here. Look at it, through this small hole. If this is the only hole that leads to this place, or that opens to the exterior, When I point the light here, when the light comes out of this place, the light ray comes out of this place, it's going to spread. It's going to spread. Okay, the spreading of light rays through a small opening is also diffraction. Diffraction of wave. It's spread. The spreading of wave when it passes through a small opening. Okay, it's also the bending of wave around obstacles. So that small opening is an obstacle, so it bends. Or through narrow opening, like I just told you, narrow opening like hole, like that small hole I just illustrated. So the interference I just explained, I told you that it's part of superimposition. Okay, when wave meets and they overlap. So we have constructive interference, which I told you that they pull closer to each other. Amplitude adds, so the amplitude increase. The circle, one circle of the wave adds, the two amplitude adds. The wave, maybe the wave is going like this, like this. The second wave will join it and continue to go in the same path like this. You know amplitude now. Two amplitude adds. Then for the destructive, amplitude cancelled. Maybe one, I told you that they will move apart. Maybe one amplitude is like this. Instead of the other one to come like this and be with it together like this, the other one will now be like this. Like this. You know the amplitude is a circle. Sorry, the other one will now be like this. So if this one is going down, this one will be going up. If this one is going up, this one will be going down. So just like that. So that's destructive interference. Now let's look at beats. Okay, beats. What is beats? Beat is the periodic derivation in loudness when two waves of slightly different frequencies interfere. So when two waves of slightly different frequencies interfere, you get beats. Slightly different. When the difference in when the difference in frequency is just slight, beat is formed. A varying loudness, a periodic varying loudness. You hear periodic, that is constructive. It's something that is arranged. Periodic, okay? So there's a slight difference in frequency. And beat frequency is equal to the difference between frequency. Okay? Beat frequency is equal to the difference between frequencies. And let's look at Doppler effects. So before we look at this Doppler effect, I'm going to tell you, for beats to be slightly different frequencies, that tells you that noise has waves of highly different frequency. Like the difference in the frequencies of the wave is very significant. Very significant. So that's how you get noise. And it's not periodic. It's not something that is constructed. Okay, that's why it's called noise. Non-directional. So the Doppler effect means apparent change in frequency of a wave due to relative motion between sources and observer. The apparent change in frequency of wave, the apparent change, the change that you see, that is obvious. The apparent change is expected, is obvious, in frequency of a wave due to relative motion between source and observer. It happened, this change in frequency happened due to what? The relative motion, that's the motion of two bodies. Yeah, you are comparing one with another between sources and observer. What are you comparing? The relative wave between the sources. Why is it relative? Because it's between the source and the observer. That's what Doppler effect. The last time, the apparent change in frequency, okay, of a wave due to the relative motion between source and observer. So what is the source? The source is where the wave is coming from. Observer is the body that the wave is transferred to. For example, you slap me. As you slap me, someone was close to me here. As you slap me, this my arm is the source of the wave. Okay? Here, my cheek is the observer of the wave. It's observed this wave. Okay? And that person that was here too, maybe when you slap me and I move my head like this, my head now hits the person. Okay? My head is now serving as another source again. Then that person that my head hits as a result of the slap and the motion of my head is also an observer. So that's it. So you have to know the difference between the source of the wave and the observer. Then source approaching. Source approaching is when the source is approaching, there is higher frequency. When the source is approaching source, there is higher frequency. Okay. That example that I just gave now, the side where we say the forte bring the slap. Okay, the frequency is higher there. You know, if you compare the frequency where the slap carry to the person where my head hits after everything don't happen. My head, because of the slap, I got my head come with it, come hit the person. You know, if you compare what I receive from the direct source approaching, the closer to the source to that one. So the closer you are to the source, or the closer the observer to the source, the higher the frequency. So the source receding, that's the farther away the observer is from the source, the lower the frequency. So that person where my head hits is quite far away from the parent source of the slap. Okay, so that's why the person is going to experience lower frequency of the wave. Okay, and as the frequency is low, the effect is also going to be lower. Okay, so let's now look at the application of the characteristics of wave. The first one here is in radar. The second one here is in astronomy. So astronomy is the study of satellites. Okay, that's astronomy. It's also used in speed, detecting speed, and so on and so forth. So this polarization Let me teach you the application of polarization because Jamb sets question from polarization. Application of polarization. Polarization is applied in glass, okay, to form spectacles, okay, sheets, the one used under sun, so that when light will fall on your sheet, sunglasses, when light will fall on the sunglasses, it reduces the intensity of the light ray that enters your eye, okay. Remember what plane polarization does, okay. It makes the transverse wave to move in only one plane, okay. So it reduces the intensity of the sunlight, the energy from the sun. When it crosses the glass, the effect will be reduced as compared to when you are not using a sunglass made from plane polarization, okay. It's also used in windows, in homes. It's just used to repair light ray, to reduce the intensity of light ray. It's also used in cars, okay, cars, windscreen, mirrors, and so on and so forth. Now that we have understood wave, its properties, its types, and classifications, let's now look at some Jamb must repeat questions to test the knowledge we've acquired so far. Jamb must repeat questions. Question 69. Which of the following best describes a wave? A. Transfer of matter from one point to another. B. Transfer of energy without transfer of matter. C. Oscillation of particles without energy transfer. D. Movement of particles in one direction. Was the answer? Drop the answer in the comment section. Question 70. A wave has a frequency of 200 Hz and wavelength of 1.5 meters. What is its velocity? A. 100 meters per second. B. 200 meters per second. C. 300 meters per second. D. 400 meters per second. Was the answer? Drop the answer in the comment section. Question 71. Sound wave in air are A. Transverse mechanical wave. B. Longitudinal mechanical wave. C. Electromagnetic waves. D. Stationary wave. Was the answer? Drop the answer in the comment section. Question 72. In a stationary wave, point of zero displacements are called what? A. Antinodes. B. Nodes. C. Crest. D. Trough. Was the answer? Drop the answer in the comment section. So before we continue with the next question, I am going to explain something that I didn't explain in the lecture, which is this node and antinode. When you see anything anti, it means that it's a point where nothing is felt. It's null. It's null. So when you see this zero here, you should know what should be there as the answer. So drop the answer in the comment section. I told you that anti means null. No, nothing. Okay? And node means that's the node. That's the place. That's the point. That's the node. In a stationary wave. Question 73. Two tuning forks of frequencies 256 Hz and 260 Hz are sounded together. What is the bit frequency? A2, B3, C4, D5. All options represented in Hz. Was the answer? Drop the answer in the comment section. Question 74. When a source of sound moves towards a stationary observer, the observer hears A. a lower frequency, B. a higher frequency, C. the same frequency, D. no sound. What's the answer? Drop the answer in the comment section. Thank you for taking this Jamb must repeat question with me. Do you need these notes? Do you need this file? Remember, this file is tailored from Jamb syllabus and is very short, straight to the point, what Jamb asks of you. It is not just past questions, it contains the topic in a short and concise way, straight to the point, what Jamb wants in the syllabus. You can get this file for just 1K. Send me a DM. My number is in my bio.